I'd like to go through and show you this delta G calculation problem, and I just want to point out where some of these values came from in each instance. So for delta H naught, we're using the formula that the sum of the delta HF of the products minus the sum of the delta HF of the reactants. The product here is the S2Cl2, but you'll notice there's 4 moles of product. So if we're talking about the sum of the product, then we need to include all the product, which is all 4 moles. That's why I'm doing 4 times, and the value here is negative 18.4 on the delta HF naught. We get that off the table, and there it is there, minus 18.4, and we know the unit is going to be kilojoules per mole at the end. These are all kilojoules per mole, by the way. But it was S2Cl2 gas. Just as a general tip, make sure that if there's more than one state present, that here's an example of that. If you've got UF6 gas, UF6 solid, those have different values. You've got to make sure you pick the right one. In this case, there is only just a one value for S2Cl2, so that one wasn't an issue. Alright, so it's 4 times negative 18.4. What I recommend is for the products, go ahead and put all of them in square brackets like this so that you can differentiate the products from the reactants. Now I've got a minus sign and another square brackets, and we're going to put all of the reactants over here in these square brackets. So we go look at the tables. We've got S8 gas. There we are, 102.3 is our value there, and there's only one of those in the reactants. There we go, 1 times 102.3 plus, and we got 4 times 0. And if you look at the tables, you'll see that chlorine gas, that's actually chlorine in its natural state. We definitely expect that to be 0 anyway, but we take a look just to be sure. And there we go, Cl2 gas, 0. Alright, remember all elements in their natural state have a heat of formation of 0 kilojoules per mole. Alright, so we go ahead, we calculate it out, it comes out to negative 175.9. Just let me point out with the significant figures, it's all based on subtraction and addition. So we're looking at the smallest number of decimal places. I want you to remember that the coefficients, the 4 and the 1 here, do not figure into significant figures because they're counting numbers. I mean, these are exact numbers of molecules. You can't have 3.5 molecules or 3.8 molecules or whatever. It'll always be a whole number. So since these are whole numbers, they don't go into the significant figures. Since we've got 1 decimal place here, 1 decimal place here, the answer is going to come out to 1 decimal place. And that's how we get that there. Delta S, we do the same thing. We go back to the table, and we use the same logic, but now we're looking at S naught, and we were looking at S2Cl2 gas, so that would be 331.5. There it is, and 4 times that again because we're looking for the sum, and then we go back to the table. S8, 430.2, and now for the Cl2, it's not going to be 0 on the entropy, it'll be 223.0, we hope, and there it is. Alright, so we copy those values directly off the chart that we're given. And again, using the same significant figure rule, we've got 1 decimal place, 1 decimal place, 1 decimal place. The answer comes out to 1 decimal place. So that's what we've got for our delta H and delta S. Now I want you to note the units on delta H as being kilojoule per mole, which we get off the table. And the S naught, though, is joules per mole per Kelvin. And that's a little bit different, so that's what we're getting off the table as well. Now we can go ahead and calculate delta G. We use delta G naught equals delta H naught minus T delta S. So we substitute in the value for delta H, minus 175.9 kilojoules per mole. Now, since we've got joules down here, we're going to need to convert that into kilojoules as well. So that's why I've multiplied it by 1 kilojoule over 1,000 joules. That gets rid of the joules and puts this into kilojoules. So we calculate that up, and see how I'm doing it separately? I do this separately because we've got a minus sign here and we've got some multiplication going on here. Since we have two significant figures and we're doing multiplication, we're going to end up with two significant figures here. Whenever you're mixing operations, you need to consider the significant figures for the first set of operations before you move on and consider the significant figures with the other set of operations. So we're doing a multiplication here, which works on significant figures, two significant figures, and then we're doing a subtraction, and that works on decimal places. So we're looking at 1 decimal place, 1 decimal place, which comes out to 1 decimal place. So that's what we have to do for the delta G. It's very important to remember that these units have to match. And when you're setting these out, I want to see this work. I want to see the units. It's for your own safety. It's so that you can make sure that you don't forget to do these kinds of conversions that are necessary during the course of the reaction.